The Milky Way is not the peaceful home you think it is. We are about to journey through 25 of its most incredible secrets, hidden in plain sight across the night sky. By the end, you will see our galaxy not as a static picture, but as a living, breathing, and often violent cosmic entity. We will uncover its cannibalistic history, meet its invisible rulers, and explore structures so vast they defy comprehension. What do you truly know about the place you call home? Our galaxy's first secret reveals a primal truth about its nature. The Milky Way is a cannibal. It did not grow gently from a cloud of gas alone. Instead, it built itself over billions of years by devouring its smaller neighbors. Right now, a dwarf galaxy called Sagittarius is in its death throes, stretched into a long, shimmering ribbon of stars that wraps around our own. This is not some ancient event from the distant past. It is happening as you look at the night sky, a slow-motion feast playing out over cosmic timescales. But the evidence of past meals is even more dramatic. Scattered throughout the galaxy's halo are strange, chaotic streams of stars, like the one astronomers call the Gaia sausage. This structure is the fossilized remnant of a colossal dwarf galaxy that smashed into the young Milky Way perhaps 10 billion years ago. The impact was so violent it did not just add stars, it fundamentally reshaped our galaxy's core, likely giving birth to the thick disk of stars we see today. This process of galactic cannibalism is the primary engine of growth for large galaxies like our own. It is how we acquired many of our stars, and it dictates our future. In about 4 billion years, the tables will turn. The Milky Way will meet its match in the Andromeda galaxy, and the two giants will begin a billion-year dance of destruction and merger, forming a new, colossal elliptical galaxy. Our home is not a serene island universe. It is a predator built from the remains of others and destined for one final, spectacular collision. This predatory history leads us to the heart of the beast itself. At the very center of our galaxy, hidden behind thick veils of dust and gas, sits a cosmic monster. This is Sagittarius, a star, a supermassive black hole with the mass of 4 million suns crushed into a single point of infinite density. We have seen its shadow, a dark circle of nothingness ringed by a fiery halo of light, captured in the landmark image from the Event Horizon telescope. It is the silent, gravitational anchor around which our entire galaxy spins. Yet for all its terrifying power, Sagittarius, a star, is strangely quiet today. It is not actively devouring large amounts of material. It is not powering a brilliant, galaxy-spanning quasar. It is, for now, a sleeping giant, but do not let its calm demeanor fool you. This black hole has a violent temper. Astronomers have found the scars of its past rage etched into the space around it. Immense, billowing clouds of gas that orbit the galactic center, like the ones known as the Fermi bubbles, show evidence of titanic explosions. These structures are the lingering echoes of colossal outbursts that occurred millions of years ago when Sagittarius, a star, was actively feeding. What does feeding mean for a black hole? It is not a gentle process. When a star or a cloud of gas drifts too close, it is not simply swallowed whole. The immense gravity stretches and shreds the material into a thin, hot, swirling disk called an accretion disk. As this superheated matter spirals inward at nearly the speed of light, it emits unimaginable amounts of energy, from X-rays to powerful jets of particles that can shoot out for thousands of light years. This is when a quiet black hole becomes the brightest object in its galaxy. Our central black hole is currently on a cosmic diet, but the evidence suggests it wakes for a violent meal every few 100,000 years. We are simply living in a relatively peaceful moment between its catastrophic feasts. Even this sleeping giant, however, is not the master of all it surveys. Our third secret forces us to abandon a fundamental image of our home. The Milky Way is not a flat, pristine frisbee of stars. It is warped, Picture a vinyl record left out in the hot sun, its edges twisted and bent into a gentle S shape. That is the true form of our galaxy's outer disk. For decades, astronomers mapped our galaxy under the assumption it was roughly flat. But new data from missions like Gaia have revealed a profound and beautiful distortion. The hydrogen gas and the stars at the very fringes of the disk, tens of thousands of light years from the center, do not lie in a neat plane. One side curls upward, the other curls downward, creating a colossal, slow-motion wave that takes hundreds of millions of years to complete a single oscillation. What could possibly bend an entire galaxy? The primary suspects are our most conspicuous galactic neighbors, the Large and Small Magellanic Clouds. These two dwarf galaxies are not just passive spectators. They are massive enough to exert a significant gravitational tug on the vast reservoir of dark matter that surrounds the Milky Way. Think of it like this: the dark matter halo is not a perfect sphere. It has a sort of wake or gravitational disturbance trailing behind the orbiting clouds. As our galaxy rotates, its outer disk, which is thinner and more flexible, gets caught in this invisible current and is slowly twisted out of shape. Another possibility is that the dark matter halo itself is lopsided, pulling the disk into this warped configuration. This is not a static deformity, it is a dynamic process, a galactic wobble induced by the dance of smaller galaxies around our own. This warping is more than a cosmic curiosity, it fundamentally changes our perspective. When we look out into the night sky, especially toward the constellations of Scutum and Norma, we are peering through this bent layer of stars and gas. It distorts our measurements of distances and the true layout of the galaxy's spiral arms. It means the Milky Way is not a rigid structure, but a flexible one, responding to gravitational forces like a vast, slow-motion sea. This subtle bend reminds us that even galaxies are not isolated islands. They are constantly shaped and reshaped by their interactions, their forms telling the story of forces we can barely perceive. This cosmic distortion directly affects our own quiet corner of the galaxy. We do not live in a bustling downtown of stars, but in a quiet galactic suburb. Our Sun, along with its planetary family, resides in a minor branch of stars called the Orion Spur. This is not one of the grand, bright spiral arms like Perseus or Sagittarius, which are illuminated by countless young, hot stars and glowing nebulae. Instead, it is a smaller, bridge-like structure that connects these two major arms. Our position here, roughly 27,000 light-years from the chaotic galactic center, is more than just an address. It might be the key reason we exist at all. This region is often called the galactic habitable zone. Think of it like the perfect distance from a campfire. Too close to the galactic core, and you are bombarded by lethal radiation from the crowded stars and the supermassive black hole. Frequent supernova explosions would sterilize any fledgling planets. Too far out in the sparse galactic outskirts, and you lack the necessary heavy elements forged in stellar furnaces and supernova to build rocky planets like Earth. Our location in this quiet spur is a cosmic sweet spot. It provides enough of the building blocks for planets and life, while offering relative peace and safety from the galaxy's most violent events. This suburban vantage point also defines our night sky. When we look toward the constellation Sagittarius, we are peering toward the brilliant, crowded core. When we gaze at the band of the Milky Way in summer, we are looking along the plane of our own local arm, seeing its accumulated starlight. Our modest celestial neighborhood offers a unique and protected view of the greater galactic metropolis, a front-row seat to the spectacle from a safe and fortunate distance. Yet this peaceful suburb, and indeed the entire galaxy, is held together by a ghost. The stars you see at night, the glowing nebulae, the vast clouds of gas, all of this luminous matter accounts for a mere sliver of the Milky Way's true substance. Perhaps 15%, the rest, the overwhelming majority of our galaxy's mass, is invisible. It emits no light, reflects no light, and absorbs no light we can detect. It is dark matter, and its presence is the most profound and unsettling secret our galaxy keeps. We know it is there because of the way things move. For a star on the outer edge of the galaxy, the rules of gravity are simple. The farther you are from the center, the slower you should orbit, just as Pluto takes far longer to circle the Sun than Mercury does. But when astronomers measured the orbital speeds of stars in the Milky Way's distant outskirts, they found something impossible. These stars were hurtling around far too fast. They were moving with such velocity that the gravity from all the visible stars and gas in the galaxy could not possibly hold them in orbit. They should have been flung off into intergalactic space long ago. The only explanation is that they are embedded within an immense spherical halo of something else, something that exerts a tremendous gravitational pull but remains completely unseen. This is the dark matter halo, a vast, shadowy sphere that envelops our entire visible galaxy like an invisible eggshell around a yolk. It is the hidden architecture, the cosmic scaffolding upon which the Milky Way is built. Without this dark matter framework, our galaxy would simply fly apart. It is the gravitational glue that holds everything together, dictating the very structure and rotation of the spiral arms we see. So what is this mysterious substance? We do not know. It is not made of atoms, not protons or neutrons or electrons. It does not interact with the electromagnetic force, which is why light passes right through it. The leading theory suggests it is a sea of exotic, as yet undiscovered particles that barely interact with normal matter except through gravity. They could be streaming through this room, through your body, right now, in unimaginable numbers without a single collision. We are essentially fish trying to understand the ocean by studying only the visible algae and plankton, completely unaware of the dense, dark water that surrounds and supports us all. This invisible ocean shapes every aspect of our galactic home, from its grandest motions to the very possibility of its existence. But this invisible ocean of dark matter is not the only unseen population in our galaxy. Drifting through the vast spaces between the stars are countless dark worlds, completely untethered from any sun. Astronomers call them rogue planets, and they are some of the loneliest objects in existence. These are not planets as we know them, orbiting a parent star in a stable, predictable dance. They are free-floating nomads cast out from their home systems by gravitational chaos and sent on an eternal journey through the interstellar void. The process that creates them is as violent as it is common. In the turbulent youth of a star system, gravitational interactions between young, massive planets can be catastrophic. One world might get flung inward toward its star, while another is hurled outward at tremendous speed, breaking free of the star's gravity entirely. It is a cosmic game of pinball with planets as the balls. Once ejected, these worlds are on their own, destined to wander the galaxy forever, illuminated only by the faint collective glow of distant stars. We know they are there because of a subtle trick of gravity called microlensing. Even a dark, invisible planet has mass, and mass bends the fabric of space-time. When one of these rogue worlds drifts precisely between us and a distant background star, its gravity acts as a tiny lens, magnifying and brightening the star's light for a brief period, sometimes just a few hours or days. By scanning the crowded star fields toward the galactic center, telescopes have caught thousands of these fleeting, telltale brightenings. The statistics are staggering. Based on these microlensing surveys, astronomers now estimate there could be billions, perhaps even trillions, of these rogue planets in the Milky Way alone. They may vastly outnumber the stars that light our sky. This means the galaxy is not primarily a collection of solar systems, but a sea of darkness punctuated by islands of light, with a hidden population of dark worlds flowing silently between them. Imagine the landscape of such a world. It is a place of permanent midnight. Without a sun, there is no day, no warmth, no sunrise or sunset. The only light comes from a starscape frozen in place, a panorama of unmoving pinpricks in an utterly black sky. Any atmosphere it once possessed has long since frozen into a global ice sheet, coating mountains and valleys in perpetual frost. Deep beneath that icy crust, however, there might be a glimmer of possibility. Tidal forces from a long-lost star or heat left over from the planet's violent formation could maintain a vast subsurface ocean of liquid water. In the absolute darkness and crushing pressure, in a place cut off from the stellar energy that fuels life almost everywhere else, who knows what strange chemistry might unfold. These rogue planets are not necessarily barren wastelands. They could be dark, aquatic abbeys, carrying the potential for life within their frozen shells on an endless voyage through the galaxy. They are a reminder that the classical idea of a habitable zone, a band of space around a star where life can exist, might be far too limited. Life, in its most tenacious forms, could be hiding in the most unexpected places, adrift in the cosmic deep. But the darkness between stars is not empty, nor is it still. It is threaded with an invisible force, a colossal web of magnetism that spans the entire galaxy. This is the Milky Way's magnetic field, a structure so vast it makes our planet's magnetic field look like a faint whisper. We cannot see it directly with our eyes, but we can map its presence through the light of distant stars. As starlight travels through the galaxy, it passes through clouds of dust that are aligned by this magnetic field. These dust grains act like tiny polarizing filters, causing the light to vibrate in a preferred direction. By measuring this subtle polarization in the light from millions of stars, astronomers have begun to trace the outline of the galactic field, revealing a complex and turbulent web. Radio telescopes add another layer to the map, detecting the faint radio waves emitted by electrons spiraling along these magnetic lines at nearly the speed of light. What emerges is a picture of a dynamic, chaotic force. The field is not neat and orderly like a bar magnet. It is twisted, tangled, and compressed by the turbulent motions of gas, the explosions of supernova, and the sheer rotation of the galaxy itself. In some regions, the field lines are stretched along the spiral arms like the grain in a piece of cosmic wood. In others, they are wildly knotted. This invisible web plays a crucial, behind-the-scenes role in some of the galaxy's most dramatic processes. It is a cosmic highway for high-energy particles. When a star explodes as a supernova, it creates a shock wave that accelerates protons and electrons to incredible speeds, creating what we call cosmic rays. These charged particles do not travel in straight lines. They are guided and confined by the galactic magnetic field, bouncing along its lines like cars on a winding, invisible freeway. Without this magnetic web, these dangerous particles would likely escape the galaxy far more quickly. The field also exerts a gentle but persistent pressure on the clouds of gas and dust where new stars are born. It can slow the collapse of a cloud, resisting gravity's pull and helping to determine the final size and number of stars that will form within it. In the deepest, darkest voids between the stars, this magnetism can even sculpt its own faint architecture. Astronomers have detected immense, delicate filaments of magnetized gas, structures light years long that glow with a faint synchrotron radiation. They are the ghostly signatures of the field's power, beautiful and ethereal traces of the force that weaves through the very fabric of our galactic home, guiding its particles and shaping its future stars from the shadows. The invisible magnetic web that shapes our galaxy finds its most extreme expression at the very place we began, the chaotic core. The region surrounding Sagittarius, a star, is not just the domain of a sleeping giant. It is a bizarre stellar factory, producing and hurling out some of the strangest objects in the Milky Way. Within just a few light years of the black hole, space is packed with stars in a density that defies belief. If you stood on a hypothetical planet there, your night sky would blaze with not thousands but millions of stars, many of them brighter than our full moon. In this gravitational pressure cooker, normal rules break down, and astronomers have found the evidence. Take the mysterious G objects. From a distance, they look like compact clouds of gas, perhaps a few times the mass of Earth. But as they swing on their elongated orbits perilously close to the black hole, they do something gas clouds should not do. They survive. A normal cloud of gas would be ripped apart by the black hole's immense tidal forces, stretched into spaghetti and consumed. The G objects, however, pass through their closest approach and emerge intact, only to return decades later. The leading theory is that these are not mere clouds, but stars shrouded in thick, extended atmospheres of dust and gas, perhaps the swollen remnants of binary stars that merged under the black hole's gravitational influence. They are cosmic phantoms, masquerading as one thing but revealing their stellar hearts only through their resilience. Then there are the hypervelocity stars. These are suns ejected from the galactic center at speeds exceeding 1,000,000 miles per hour, so fast they are on a one-way trip out of the Milky Way entirely. They are the products of a gravitational slingshot. Imagine a binary star system, two stars orbiting each other, wandering too close to Sagittarius, a star. The black hole's gravity can violently tear the pair apart, capturing one star into a tight orbit and flinging the other away with such ferocious energy that it achieves escape velocity from the whole galaxy. We have tracked these stellar outlaws, like one known as S5HVS7, as they race through the galactic halo, destined for the emptiness of intergalactic space. But perhaps the deepest puzzle in this crowded core is the presence of stars that, by all rights, should not be there at all. Scattered in tight, orderly rings just a light year from the black hole are dozens of young, massive hot stars. This is a profound mystery. The environment so close to a supermassive black hole is one of immense tidal forces and searing radiation, a place where the vast clouds of gas needed to form stars should be shredded and dispersed. Yet these brilliant blue stars are there, shining defiantly. How did they get there? One radical idea is that they did not form in place from a collapsing cloud, but were born through a process of direct collision and merger. In the stellar traffic jam of the galactic center, lower mass stars could have been forced together by the black hole's gravity, piling on mass until they ignited as the brilliant giants we see today. Another theory suggests a gas cloud was compressed not by its own gravity, but by the sheer external pressure of the environment, triggering a frantic burst of star formation in what should have been a stellar dead zone. These stars are cosmic rule breakers, their very existence forcing us to rewrite the textbook on how and where stars can be born. The galactic center is a laboratory of extremes, a place where gravity writes its own bizarre laws and creates wonders we are only beginning to comprehend. But the galactic center's violence does not stay confined. Its outbursts can leave scars on a scale that dwarfs everything we have discussed so far. Emanating from the very heart of the Milky Way, stretching for 25,000 light-years both north and south of the galactic plane, are two colossal spheres of searing energy. These are the Fermi bubbles, first discovered in 2010 by the Fermi Gamma Ray Space Telescope. To grasp their size, consider that the entire visible disk of our galaxy is about 100,000 light-years across. These bubbles, named for the telescope that found them, reach halfway from the center to the edge. They are not made of stars or gas you can see with an optical telescope. Instead, they are vast, faint structures glowing in the highest energy form of light, gamma rays. They are essentially two giant, ghostly balloons of ultra-hot plasma, inflated by some unimaginably powerful event. For years, they remained completely hidden, invisible to every form of observation until we had a telescope specifically designed to scan the sky for gamma rays. Their discovery was a shock, revealing that our galaxy's recent past was far more explosive than anyone had guessed. So what could have created such immense structures? The prime suspect is, of course, our central supermassive black hole, Sagittarius, a star. The leading theory suggests that several million years ago, the black hole awoke from its slumber for a monumental feast. A vast cloud of gas, or perhaps an entire star cluster, wandered too close. As this material was torn apart and spiraled into the accretion disk, it did not just shine brightly. A significant portion of the energy was channeled into two opposing, pencil-thin jets of relativistic particles, shooting out perpendicular to the galactic disk at nearly the speed of light. These jets, acting like cosmic blowtorches, plowed into the halo of gas surrounding the Milky Way, inflating these gigantic, bubble-like cavities and filling them with swirling, magnetized plasma. The event would have been a brief but terrifying beacon, visible across the local universe, but there is another compelling suspect. The same region that hosts the black hole is also a frenetic stellar nursery. It is possible that not one, but hundreds or thousands of massive stars were born in a short, intense burst of star formation. These stars live fast and die young, exploding as supernova in rapid succession. The combined force of all these simultaneous explosions could have created a titanic, spherical shockwave, a galactic superwind that blew these bubbles outward. This would be a case of stellar violence on an industrial scale, a coordinated detonation powerful enough to reshape the galaxy's atmosphere. The true answer might even be a combination of both events, a black hole outburst energized by a wave of supernova. What is certain is that the Fermi bubbles are a fossil record of a cataclysm. They are the lingering breath of a galactic-scale eruption, a reminder that the quiet center we see today is merely the calm after a storm that once lit up the cosmos. That galactic-scale eruption left more than just bubbles as its monument. It helped fill an even vaster and more fundamental structure, one that encases our entire galaxy like a steamy, invisible atmosphere. The Milky Way is not floating in a cold, empty void. It is surrounded by an immense halo of superhot gas, a seething reservoir of matter with a temperature measured in millions of degrees. We cannot see this halo with optical telescopes, for it does not glow with visible light. Instead, it betrays its presence by what it steals. When astronomers point X-ray telescopes at brilliant, distant quasars, the luminous cores of active galaxies billions of light-years away, they sometimes see a telltale dip in the quasar's high-energy signal. That dip is the fingerprint of our own galactic halo. As the quasar's X-rays journey across the universe toward us, they must pass through this massive, diffuse cloud of hot gas surrounding the Milky Way. Atoms within the halo, like highly charged oxygen and iron, absorb specific wavelengths of this X-ray light, creating dark lines in the spectrum. It is akin to holding a colored filter up to a bright light, seeing which colors are blocked. By analyzing these absorption lines, scientists can measure the halo's composition, temperature, and staggering scale. This gaseous envelope is colossal, extending for hundreds of thousands of light-years from the galactic disk, likely farther than even the Magellanic Clouds. It contains enough ordinary matter to forge billions of new stars, yet it is so diffuse that a cubic meter of this space would contain only a few atoms, a vacuum far better than anything we can create on Earth, but so vast that its total mass is immense. This halo is not a static blanket. It is a dynamic galactic recycling plant, a crucial part of the ecosystem that governs the life and death of stars. Where does all this hot gas come from? Its primary source is the collective fury of dying stars. Every supernova explosion in the disk of the Milky Way is a titanic event that does more than just destroy a star. It blasts its enriched remains oxygen, carbon, iron, and other heavy elements forged in its core out into space at tremendous speeds. This metal-rich debris, heated to millions of degrees by the shockwave, punches its way out of the galactic disk and into the halo. The Fermi bubbles from the galactic center are a dramatic example of this process, a concentrated injection of energy and matter. But countless smaller supernovae over billions of years have contributed to filling this atmospheric reservoir. Once in the halo, the hot gas does not necessarily escape forever. Gravity still has a hold on it, As this material slowly cools over cosmic timescales, it can condense into denser clouds that then rain back down onto the galactic disk, pulled by the Milky Way's gravity. This is known as a galactic fountain. Picture a geyser erupting from the disk, sending hot, metal-enriched material high into the halo, where it cools and falls back as a shower of cooler gas clouds. This cycle is the galaxy's way of recycling its heavy elements. The iron in your blood, the oxygen you breathe, the calcium in your bones. These atoms were cooked inside stars, blasted into space by supernova, lofted into the hot halo, and later rained back down to be incorporated into new stars, planets, and eventually life. This halo, therefore, is more than just an atmosphere. It is the galaxy's long-term memory and its future fuel supply. The gas that rains back down is seed material for the next generation of stars, enriched with the ashes of its predecessors. Our entire solar system was likely born from a cloud of gas that had gone through this cosmic recycling process multiple times. The hot halo is the great intermediary, the place where the galaxy processes its past to build its future, a silent, shimmering engine of rebirth that surrounds us all. Our galaxy's core hides a cosmic traffic circle, and at its center is not a roundabout but a straight, dense bar. This is the Milky Way's central bar, a vast structure made of billions of ancient red stars stretching for thousands of light years. For most of astronomical history, we could not see this bar directly because our solar system is embedded within the dusty galactic plane, looking out through a crowded, murky disk. Its existence was long debated, a theoretical suggestion to explain strange motions of stars and gas. But modern infrared surveys, which can pierce the dust, have now confirmed it. We live in a barred spiral galaxy. Picture the core not as a simple sphere of stars around the black hole, but as a rigid, elongated rectangle of old suns, rotating together like a solid piece of celestial machinery. This bar is the hidden engine driving much of the galaxy's inner dynamics. Its immense gravity acts as a cosmic pump, redirecting the flow of stars and gas. As the bar rotates, its gravitational field creates a kind of traffic pattern. It funnels interstellar gas and dust from the outer regions inward along its leading edges, channeling this raw material on a one-way trip toward the galactic center. This process is crucial for feeding the central black hole, Sagittarius a star, and for fueling the intense bursts of star formation that occur in the innermost nuclear ring. Without this bar, our galactic core might be far quieter and more starved, but the bar's influence extends far beyond the inner few thousand light years. It directly shapes the grand spiral arms we see from our vantage point. The arms themselves are not permanent structures made of the same stars, but density waves like traffic jams moving through a highway. The rotating bar, with its powerful gravitational pull, is thought to be the primary driver that sets up and sustains these waves. It essentially orchestrates the majestic spiral pattern, determining where the waves of compressed gas will trigger the birth of new, brilliant stars. Our position within the Orion Spur means we are observing this grand design from within the traffic jam, our view shaped by the relentless, rotating pull of that central bar of ancient stars. The ancient bar orchestrating our galaxy's spiral arms is itself a relic of a more violent past. Our next secret reveals that we are not just living in a cannibal galaxy, but are literally surrounded by its digested meals. Scattered throughout the vast spherical halo that envelops the Milky Way are the fossilized remains of entire galaxies consumed long ago. This field of study is called galactic archaeology, and it allows us to read our own history written in the motions and chemistry of ancient stars. The most dramatic of these fossils is known as Gaia Enceladus, sometimes called the Gaia sausage. This is not a single visible object, but a distinct population of tens of millions of stars, now seamlessly blended into our halo. They were identified not by where they are, but by how they move. Data from the European Space Agency's Gaia mission, which precisely maps the positions and velocities of over 1 billion stars, revealed something astonishing. A huge group of stars in the halo were not moving in random orbits. Instead, they were streaming together on highly elongated radial paths, plunging toward the galactic center and then swinging far out again like a swarm of bees on chaotic trajectories. This distinctive motion was the first clue. The second clue came from their chemical makeup. Stars act as cosmic time capsules, preserving the composition of the gas cloud from which they formed. The stars from Gaia Enceladus are metal-poor, meaning they contain very low amounts of elements heavier than hydrogen and helium. This tells us they were born in the early universe, before many generations of stars had lived and died to enrich the cosmos with these heavier elements. Put together, the story becomes clear. Between 8 and 10 billion years ago, a substantial dwarf galaxy, perhaps 1/4 the mass of the young Milky Way itself, was on a collision course. This was no glancing blow. It was a head-on catastrophic merger. The smaller galaxy, Gaia Enceladus, was utterly torn apart by our galaxy's gravity. Its stars were not neatly absorbed, they were violently scattered, their orderly orbits shattered and transformed into the wild, radial paths we see today. The collision did more than just add stars. It is believed this immense impact fundamentally reshaped the Milky Way, possibly triggering the formation of the thick disk of older stars and even contributing to the creation of that central stellar bar. When you look up at the night sky, you are not just looking at the Milky Way, you are looking at a galactic hybrid. Some of those faint, distant points of light in the halo are not native to our galaxy. They are survivors from a different, long-dead island universe captured forever within our own. They are the ghosts of galaxies past, and their silent testimony is rewriting the story of our cosmic home. These ancient stellar fossils force us to reconsider the very structure we see when we gaze at the Milky Way's band of light. The majestic spiral arms, those sweeping arcs of stars and glowing nebulae that define our galaxy's portrait, are not what they seem. They are grand and beautiful illusions. The stars within an arm are not fixed in place like gems set in a celestial bracelet. Instead, the spiral arms are density waves, moving through the galactic disk like slow-motion traffic jams on a cosmic freeway. Picture a wave moving through a crowded sports stadium. The people stand up and sit down, but they do not move from their seats. The wave itself travels around the stadium, while each individual person remains in place. A spiral arm works in a similar way. It is a region of compressed space, a gravitational ripple where the density of stars and gas is temporarily higher. As the galaxy rotates, stars and gas clouds enter this dense region, slow down and pile up. This compression triggers the collapse of giant gas clouds, igniting the brilliant, short-lived blue stars and glowing nebulae that outline the arm in light. Then, over millions of years, these stars move through and out the other side of the wave, continuing on their orbits. The most massive blue stars burn out and explode as supernova long before they leave the arm, which is why we see the spiral pattern so clearly traced in light. It is literally a map of where star formation is currently happening. The wave itself, however, moves at a different, slower speed than the stars and gas. This explains a profound mystery. If the arms were permanent structures made of the same stars, the galaxy's rotation would wind them up tightly over a few 100 million years, like strands of caramel spun around an apple. We would see a galaxy of tightly wound coils, not the grand, open spirals we observe. The density wave theory solves this. It is the pattern that persists, not the participants. Our own sun and our solar system have passed in and out of these spiral arms many times throughout the galaxy's history. We are currently cruising through a relatively sparse region, the Orion Spur, having recently left the inner edge of the Perseus Arm. This cosmic traffic pattern is not just a curiosity, it dictates the rhythm of life in the galaxy. Passing through a dense spiral arm means encountering more interstellar gas, more cosmic rays, and a higher chance of drifting near a lethal supernova. Some scientists speculate that Earth's historical ice ages could be linked to our solar system's periodic passage through these denser, more dangerous regions, where increased cosmic radiation might affect our climate. The spiral arms are not just pretty pictures, they are the galaxy's heartbeat pulsing with star birth and death, and their gentle gravitational waves shape the long-term fate of every star, including our own, on its endless journey around the galactic center. This cosmic traffic pattern places us right beside a stellar highway under construction. While we orbit in the quiet Orion Spur, astronomers have mapped a dazzling new structure literally pointing in our direction. It is called the Cepheus Spur, a recently identified branch of young, hot stars and glowing gas that juts out from our local Orion arm like a celestial finger aimed nearly at our solar system. This is not a distant feature, it is part of our immediate galactic neighborhood, giving us an unprecedented front row seat to the raw process of star birth. The spur is named for the constellation Cepheus, where it appears most prominent, and it is traced by the brilliant blue light of OB stars. These are the titans of the stellar world, massive stars that burn fiercely and die young, illuminating the vast clouds of hydrogen gas from which they were born. Because these stars are so luminous and so short-lived, they act as perfect markers, outlining the spur's structure and confirming it is a region of very recent, ongoing creation. To stand on a hypothetical world within the Cepheus Spur would be to witness a celestial fireworks factory in full operation. The sky would be dominated by the deep, crimson glow of immense nebulae like the Heart and Soul nebulae, vast clouds where radiation from newborn stars is causing the surrounding gas to fluoresce in brilliant pinks and reds. Dark, silhouetted knots known as Bok globules would drift across that glowing backdrop. These are the dense, cold cocoons of gas and dust where new stars are currently condensing, hidden from visible light but soon to burst forth. This proximity transforms the spur from an abstract map feature into a living laboratory. We can study individual stellar nurseries within it in exquisite detail, watching as powerful stellar winds from young stars sculpt the surrounding gas into fantastic pillars and caverns, and observing how the shockwaves from supernova trigger the next round of star formation in a nearby cloud. The Cepheus Spur is essentially a snapshot of the spiral arm density wave in action, frozen in a moment of prolific creation happening right next door. Its orientation toward us is a stroke of cosmic luck, offering a clear, unobstructed view into the mechanisms that build the galaxy itself, all happening in our own backyard. The brilliant stellar nurseries of the Cepheus Spur are just one small part of a much larger, breathless environment. Our galaxy is not merely filled with stars and gas, it is actively exhaling, blowing colossal bubbles on scales that boggle the mind. These are not soap bubbles, but immense structures of searing energy, and they reveal a dynamic, multi-layered atmosphere we are only beginning to map. You have already met the most famous of these, the Fermi bubbles, those twin spheres of gamma-ray light stretching far above and below the galactic center are just one slice of a much richer story. Recently, an X-ray telescope named eROSITA revealed a stunning counterpart. It discovered an even larger set of bubbles, perfectly aligned with the Fermi structures but glowing in soft X-rays. They are like a faint, hot ghost enveloping the gamma-ray bubbles, suggesting a single, ancient cataclysm at the galactic center created both. The hotter X-ray, emitting gas, likely outlines the shock front, the outer boundary of the explosion, while the gamma rays come from fast-moving particles trapped inside, like the foam inside a wave. But the bubble blowing is not confined to the galaxy's core. We are living inside one ourselves. Our solar system currently drifts through a region called the local bubble, a vast, irregular cavity in the interstellar medium about 1,000 light-years across. It is not empty, but filled with an extremely thin, million-degree gas. The walls of this bubble are traced by the bright stars of many nearby constellations and glowing clouds of cooler gas like the Orion Nebula. How did this local cavity form? It was sculpted by not one, but a series of supernova explosions that occurred over the past 10 to 20 million years. Massive stars that once lived in a loose cluster together reached the ends of their lives in a cosmic chain reaction. Each explosion sent a powerful shockwave through space, sweeping up interstellar gas and dust into a dense shell and hollowing out the region we now inhabit. We are essentially floating in the aftermath of a local stellar catastrophe, a testament to the fact that even our quiet corner of the galaxy is shaped by violent cyclical events. These bubbles, from the galactic scale Fermi structures to our own local bubble, paint a new picture of the Milky Way. They show a galaxy with a complex, layered atmosphere, where energy from star death and black hole outbursts carves out cavities, drives winds, and redistributes matter. It is a ceaseless process of inflation and collapse, where old bubbles eventually rupture and new ones form, keeping the interstellar medium in a state of perpetual, churning motion. This is the galaxy breathing in cycles lasting millions of years. Breathing within these bubbles, we are still confined to the thin plane of the galactic disk. But our galaxy's true domain extends far beyond this starry pancake, into a vast and mostly empty frontier. Encasing the entire visible Milky Way is an immense spherical wilderness known as the galactic halo. This is not a place of bright nebulae and bustling star formation. It is a realm of profound solitude, a sparse three-dimensional cloud where stars are separated by light years of near-perfect vacuum. The halo is the galaxy's attic, filled with ancient relics and its heaviest secrets. Its most luminous inhabitants are the globular clusters, dense balls of up to 1 million stars each, orbiting the galactic center like a swarm of bees. These clusters are fossils from the universe's youth, over 12 billion years old, containing stars that formed before the Milky Way's disk even settled into its current elegant shape. They are time capsules of pure, primordial hydrogen and helium, their chemistry telling us about the conditions in the infant cosmos. Between these glittering clusters drift isolated, ancient suns, moving on long, looping orbits that take them plunging through the disk and then far out into the emptiness. This entire sparse population of stars and clusters is just the visible tracer, the glitter sprinkled within something far more massive. The halo is overwhelmingly dominated by the invisible ocean of dark matter, whose gravitational pull is the only thing keeping this whole structure from flying apart. The scale is almost incomprehensible. While the bright disk of the Milky Way is about 100,000 light-years across, the dark matter halo extends for perhaps 1 million light-years in all directions. Our entire visible galaxy is just a small, bright ornament embedded in the heart of this colossal, invisible sphere. This immense gravitational field is the master of our local cosmic neighborhood. It dictates the fates of the satellite galaxies that orbit us, like the large and small Magellanic Clouds. They are not simply passing by, they are trapped, forever circling within the Milky Way's vast, unseen grasp. The halo's gravity stretches and distorts these dwarfs, slowly pulling them apart into stellar streams, the very process of galactic cannibalism we witnessed earlier. To understand the halo is to understand the raw foundation of the Milky Way. Its ancient stars hold the chemical recipe of the earliest times, recording the galaxy's assembly before the first spiral arm ever turned. Its immense dark matter scaffold defines our galaxy's very identity and power. We live our lives in the bright, thin metropolitan disk, but we are all governed by the laws of a much larger, darker, and older country that surrounds everything we see. That immense dark halo is not a serene frontier. It is a battlefield, and our galaxy's largest satellite is currently losing the war. Orbiting the Milky Way at a distance of about 160,000 light-years is the Large Magellanic Cloud, a brilliant, irregular galaxy visible from the southern hemisphere. For eons, it was considered a peaceful companion, a beautiful but passive cloud of stars. We now know it is anything but passive. The Large Magellanic Cloud is a heavyweight containing perhaps 10 billion stars, and it is massive enough to exert a profound gravitational influence on our own galaxy. Its passage is not gentle. As it moves through the Milky Way's vast dark matter halo, it creates a powerful wake, a gravitational disturbance that tugs and twists the very fabric of our galaxy. This is the primary force behind the grand warp we discovered in the Milky Way's outer disk. Think of a speedboat cutting through a still lake. The boat creates a wake that makes floating buoys bob and sway. The Large Magellanic Cloud is that cosmic speedboat, and its gravitational wake is violently rocking the outer edges of our galactic disk, bending it into that slow, majestic S-curve. But the damage goes deeper than a simple warp. This interaction is also stripping the Large Magellanic Cloud itself of its gas and stars, creating a spectacular, shimmering river of material known as the Magellanic Stream. This ribbon of hydrogen gas stretches for hundreds of thousands of light years across the southern sky, a visible scar of the ongoing gravitational struggle between the two galaxies. Yet this satellite is fighting back in a way we never anticipated. Recent studies suggest the Large Magellanic Cloud is so massive that it is not just distorting the Milky Way's disk, it is actually pulling our entire galaxy off-center. The precise, balanced orbit of our solar system around the galactic core may be subtly shifting because of the gravitational pull of this one companion. We are not watching a static dance, we are witnessing a dynamic, chaotic tug of war on a cosmic scale. The future of this relationship is certain, and it is grim for the smaller partner. The Large Magellanic Cloud is on a decaying orbit, slowly spiraling inward toward the Milky Way. In perhaps 2 billion years, it will venture too close. The tidal forces that are currently stretching it into streams will become overwhelming. It will be torn apart, its stars scattered and absorbed into our halo, its gas funneled toward the center to fuel new generations of stars. It will cease to be an independent galaxy and become just another fossil in the Milky Way's archaeological record, another chapter in our cannibalistic history. For now, it serves as a brilliant preview, a twin galaxy in its prime, showing us the vibrant, chaotic processes of star birth and death in a smaller, more accessible package. But its fate is sealed. It is a dying galaxy, and its final act is to reshape the very giant that will consume it. The battlefield of the galactic halo is silent, but the disk of the Milky Way sometimes screams. Across the cosmos, astronomers have detected the most powerful and mysterious radio signals in the universe, brief blasts of energy that outshine entire galaxies for a few thousandths of a second. These are fast radio bursts, and for years their origin was one of astronomy's greatest puzzles. They seem to come from unimaginable distances far beyond our own galaxy, hinting at cataclysmic events in the deep universe. Then, in April 2020, a detector on Earth picked up a signal of a different kind. It was a simultaneous blast of X-rays and gamma rays, and it came not from a distant galaxy, but from inside our own Milky Way. The source was traced to a known object in our galactic backyard, a highly magnetized neutron star called a magnetar. This was the smoking gun. For the first time, we had directly witnessed a fast radio burst being born within our own galaxy. What are these signals? They are pulses of radio waves so intense that a single millisecond burst can release more energy than our sun puts out in 80 years. They flash once and are usually gone forever, though some sources have been caught repeating the performance. The discovery that at least some of them come from magnetars was a breakthrough. A magnetar is a neutron star, the collapsed core of a massive star that exploded as a supernova, but taken to an even more extreme level. It possesses a magnetic field 1,000 trillion times stronger than Earth. This magnetic field is so unimaginably powerful that it can literally twist the star's solid crust, causing starquakes that release titanic bursts of energy. Picture the entire crust of a city-sized object, made of material harder than diamond, cracking under magnetic strain and releasing in an instant more energy than all the earthquakes in human history combined. That energy floods into space as a focused beam of radio waves, a fast radio burst. The fact that we detected one from within the Milky Way, linked to a specific magnetar, tells us that these exotic stellar corpses are certainly one source of these cosmic sirens. But the mystery is not fully solved. The local burst from our galactic magnetar was actually weaker than the more common, distant FRBs. This suggests that while magnetars can produce them, the most extreme versions detected from other galaxies might require an even more violent trigger, perhaps involving a magnetar being swallowed by a black hole or two neutron stars colliding. So the Milky Way's own magnetars give us a crucial key, a nearby laboratory to study the physics of these dazzling explosions. They remind us that our galaxy is not just a collection of quiet stars, but a place where the most ferocious magnetic fields in the universe can snap without warning, sending whispers of their violence across the cosmos. The violent flashes of magnetars are brief sparks within a far larger, more pervasive environment. The space between stars is not a perfect vacuum. It is filled with a complex, dynamic mixture of gas and dust, a cosmic ecosystem astronomers call the interstellar medium. This is the raw material of the galaxy, the stuff from which every star and planet is born and to which they all return. To call it empty is like calling the ocean empty because you cannot see the plankton. It is a rich, structured, and multi-layered habitat existing in several distinct phases simultaneously, each with its own temperature, density, and role in the galactic life cycle. The coldest and densest phase is where the magic of creation begins. These are the dark molecular clouds, vast, frigid complexes that can span hundreds of light years. Temperatures here plunge to just a few degrees above absolute zero. Within these cosmic freezers, hydrogen atoms pair up to form hydrogen molecules, and they mingle with fine grains of silicate and carbon-rich dust. This dust is not like household dirt. Each grain is microscopic, perhaps 1,000 times smaller than a grain of sand, and it acts as a protective shield, blocking harsh starlight and allowing molecules to form and cluster in the deep cold. These clouds are the stellar nurseries. Gravity slowly works on their densest knots, causing them to collapse. As a knot shrinks, it spins faster and heats up, eventually igniting nuclear fusion at its core. A new star is born. The famous pillars of creation in the Eagle Nebula are a stunning example of this process, towering columns of cold gas and dust being sculpted and eroded by the fierce radiation from nearby newborn stars, even as new stars condense within their dark tips. But these dark clouds are just one part of the story. Most of the volume of the galactic disk is filled with a warmer, more diffuse phase, the atomic hydrogen gas. Here, hydrogen exists as single, neutral atoms. This gas is warmer, perhaps 100 degrees above absolute zero, and far less dense. It fills the space between the molecular clouds like a vast, thin fog. We can map this atomic hydrogen across the entire sky because it emits a faint, characteristic radio signal at a wavelength of 21 centimeters. This signal has allowed astronomers to trace the Milky Way's spiral structure as the gas piles up in the density waves of the arms. This warm atomic layer is the reservoir, the galactic feedstock from which the denser molecular clouds slowly condense over millions of years. Then there is the most energetic phase, the hot ionized plasma. This is gas that has been heated to temperatures of 1,000,000 degrees or more, either by the blast waves of supernova or by the intense ultraviolet radiation from massive stars. At these temperatures, atoms are ripped apart. Electrons are stripped from their nuclei, creating a soup of charged particles, a plasma. This phase fills the cavities of bubbles like our local bubble. It is the exhaled breath of the galaxy's most violent events. This hot plasma is so tenuous that a volume the size of a typical classroom might contain only a single atom, yet it occupies enormous regions of space. These three phases, cold molecular, warm atomic, and hot ionized, are not isolated. They constantly interact and transform into one another in a grand galactic recycling loop. A supernova shockwave slams into a warm atomic cloud, compressing it and triggering the formation of a cold molecular cloud, which then forms stars. Those massive stars then flood their surroundings with ultraviolet radiation, ionizing the gas around them and creating brilliant bubbles of hot plasma, which eventually cool and recombine back into atomic gas. This cycle has been turning for billions of years. Every atom in your body, except for the primordial hydrogen, was forged inside a star and then expelled into this interstellar medium. It drifted through these different phases, perhaps spending time in a cold cloud, being warmed by starlight and heated by a supernova shock, before eventually becoming part of the cloud that collapsed to form our Sun and its planets. The space between the stars is not empty. It is a cosmic womb, a recycling center, and a graveyard all in one. It is the fundamental substrate of the galaxy, and its quiet, complex chemistry is the reason we are here at all. Our own solar system is not a passive passenger on this galactic journey. While we orbit the galactic center once every 230 million years, our path is anything but a smooth, flat circle. The Sun, carrying all its planets with it, is on a profoundly wobbly ride. It does not stay neatly within the plane of the Milky Way's disk. Instead, our entire cosmic neighborhood bobs up and down through the galactic plane like a carousel horse on a slow, majestic track. Imagine the bright band of the Milky Way as a flat road. Right now, we are driving slightly above it. In about 15 million years, we will cross down through the middle of that starry road. Then we will continue descending, reaching our maximum distance below the plane, before turning around and climbing back up to cross it again. This complete vertical oscillation from peak to peak takes between 60 and 70 million years. We are quite literally surfing a galactic wave with a period longer than the age of the dinosaurs. This rhythmic motion is not just a celestial curiosity. It places us in different galactic environments over deep time, and some scientists wonder if this could leave a mark on our own world. When the solar system is at the peak or trough of its oscillation, farthest from the crowded galactic midplane, we are relatively isolated. But when we plunge through the dense star fields and molecular clouds of the disk itself, we enter a more hazardous neighborhood. The density of interstellar material increases. The chances of a close encounter with another star or drifting through a particularly dense cloud of gas and dust go up. Could this periodic immersion trigger events on Earth? One compelling hypothesis links this vertical motion to our planet's climate history. Geological records show a rough cycle of increased comet impacts and major mass extinction events about every 30 million years. That timing is eerily close to the half period of our solar system's vertical oscillation. As we pass through the densest part of the galactic disk, the theory suggests the increased gravitational tug from concentrated mass could disturb the distant Oort cloud, that vast spherical shell of icy bodies at the very edge of our solar system. This gravitational nudge could send a shower of long-period comets hurtling inward, some of which might cross Earth's path with devastating consequences. The evidence is not yet conclusive, but the idea is powerful. It suggests that the grand, slow dance of our galaxy might directly influence the biological story of our planet. Our solar system's gentle wobble could be a cosmic metronome, ticking off eras of stability and chaos over hundreds of millions of years. We are not merely circling the center, we are weaving through the galaxy's layers, and with each crossing, we roll the dice on a new chapter of life's history. Our solar system's wobbling path is a gentle ripple compared to the gravitational maelstrom at the galactic core. There, just a few light years from the destructive pull of Sagittarius, a star, a ring of monstrous young stars defies all logic. It is a cosmic donut of brilliant blue giants, each one many times more massive and luminous than our Sun. orbiting the black hole at a perilously close but stable distance. This torus of titans presents one of the Milky Way's most stubborn mysteries. How did these stars form in a place that should be a stellar dead zone? The environment here is brutally hostile. The black hole's immense tidal forces should shred any vast, cool cloud of gas long before it could collapse to form stars. The radiation from the crowded stellar metropolis and from the black hole's own past outbursts would heat and disperse star-forming material. It is like trying to light a candle in the heart of a hurricane. Yet the stars are undeniably there, shining with the fierce blue-white light of youth, their chemistry showing they were born from the very gas that swirls near the center. Astronomers have wrestled with two main theories, each more dramatic than the last. The first is a story of forced marriage. In the stellar traffic jam around the black hole, close encounters between older, lower-mass stars could be common. Two stars might gravitationally capture each other, spiraling together in a violent merger. The resulting combined star would be more massive, hotter, and brighter, mimicking the appearance of a young star. This process could build up these blue giants through a series of cosmic collisions, a frantic game of stellar bumper cars orchestrated by the black hole's deep gravity well. The second theory is even more extreme. It suggests a giant molecular cloud was caught in a vice. Perhaps such a cloud was on a trajectory that sent it plunging toward the center. As it approached, it would not have collapsed under its own gravity in a calm, isolated process. Instead, the immense external pressure from the surrounding hot gas and the sheer gravitational compression from the black hole itself could have squeezed the cloud from all sides. This violent overpressure might have triggered a frantic, fireworks-like burst of star formation all at once, like crushing a lump of coal in your fist and turning it into a diamond in an instant. This would have been a uniquely chaotic and intense birthing event, creating an entire generation of massive stars in a single, catastrophic episode. These stars are not just curiosities, they are crucial probes. Their orbits allow us to map the precise gravitational field around Sagittarius, a star with incredible accuracy, confirming the black hole's mass and even testing Einstein's theory of general relativity. They are also living on borrowed time. Their great mass means their nuclear furnaces burn furiously, and they will exhaust their fuel in just a few million years, ending their lives not with a quiet fade, but in spectacular supernova explosions that will momentarily outshine the entire galactic center. Their very existence, a ring of brilliant defiance so close to the abyss, forces us to reconsider the limits of star formation and the raw, creative power of the galaxy's most destructive environment. The brilliant, defiant stars orbiting the black hole highlight a galaxy rich with mysteries, but some of the greatest puzzles involve what we cannot see at all. Our galaxy's vast dark matter halo should be teeming with thousands of small, dense clumps of that invisible substance, according to our most sophisticated supercomputer simulations of cosmic structure. This is a fundamental prediction. Wherever you have a large halo of dark matter like the Milky Way's, gravity should cause it to fragment into a vast swarm of smaller subhalos like lumps in a thick gravy. And because dark matter's gravity pulls in ordinary gas, many of these clumps should have gathered enough material to spark star formation, becoming small, faint satellite galaxies orbiting our own. The math is clear. We should be surrounded by a bustling cloud of hundreds, perhaps even thousands of these tiny galactic companions. Yet when we look, we find only a few dozen. This glaring mismatch between theory and observation is called the missing satellites problem, and it has haunted cosmologists for decades. Where did all those small galaxies go? One compelling answer is that we have been looking with the wrong eyes. Our traditional surveys scanned the sky for collections of stars bright enough to stand out against the black. But what if the smallest dark matter clumps never gathered enough gas to make many stars? Or what if the first bursts of star formation in these tiny galaxies were so feeble or so long ago that they have since sputtered out entirely? We would be left with what astronomers call dark galaxies, halos of pure dark matter, holding perhaps only a handful of ancient dim stars or even none at all. These would be essentially invisible to our telescopes, ghostly islands of shadow circling the Milky Way. Recent, deeper surveys have started to find more of these ultra-faint dwarfs, some containing only a few hundred stars lost in the vastness of the halo. Each new discovery chips away at the discrepancy, suggesting many satellites were not missing but merely hiding in the darkness, waiting for more sensitive instruments to reveal them. But there is a more radical possibility. The problem might not be with our eyes, but with our understanding of dark matter itself. The standard model assumes dark matter is cold and slow-moving, which naturally forms these abundant small-scale clumps. But what if dark matter is slightly warmer or interacts with itself in subtle ways? Even a tiny amount of internal interaction could smooth out those smallest lumps, preventing them from ever forming. It is the difference between a fine, clumpy powder and a smooth, flowing liquid. If dark matter has any such properties, it would erase the smallest subhalos from the simulation, bringing the predicted number much closer to the dozens we actually observe. This makes the missing satellites not just a counting exercise, but a potential key to unlocking the true nature of the universe's dominant substance. Every faint smudge of stars we discover on the edge of visibility, and every empty patch of sky where we find none, is a clue in this grand detective story. The halo is not simply empty, it is a testing ground for the deepest laws of the cosmos, and the answer to what fills it will reshape our understanding of everything. The search for hidden worlds does not end at the edge of our solar system. Far beyond Neptune, in the frigid darkness where the sun is just a particularly bright star, astronomers have found a strange pattern. Several small, icy objects out in the Kuiper belt share a peculiar alignment, their orbits clustered in a way that suggests the gentle but persistent tug of something much larger. This is the clue that points to Secret 23. Our solar system might still hold a giant, undiscovered planet, and its story could be written by the galaxy itself. This hypothetical world is called Planet 9. We are not talking about a small, rocky body like Pluto, but a potential super-Earth or mini-Neptune, perhaps 5 to 10 times the mass of our own world, orbiting on a slow, elliptical path hundreds of times farther from the Sun than Earth. Its gravitational influence, theorists propose, is what herds those distant Kuiper belt objects into their odd, grouped orbits. But where could such a planet have come from, and how could it remain stable in such a distant, lonely realm? The answer may lie not with the Sun, but with the Milky Way. At these incredible distances, the Sun's gravity grows incredibly weak. The gravitational dominion of our star does not simply stop, it gradually gives way to the combined pull of the entire galaxy. This creates a subtle background force known as galactic tides. Picture the solar system not as an isolated island, but as a raft floating on a vast, gentle ocean. The ocean is the Milky Way's gravitational field. As the raft bobs on the water, every part of it feels the rise and fall of the waves. In the same way, every object in our outer solar system feels the slight, persistent tug of the galaxy's mass. This tidal force is extraordinarily faint, but over billions of years it can sculpt orbits. It acts as a cosmic shepherd, preventing the most distant objects from drifting away entirely and potentially shaping the paths of those we see. This is where Planet 9 becomes a galactic story. For such a distant, massive planet to have a stable, billion-year orbit, it must be in a kind of gravitational harmony. Its long, elliptical path must be oriented in a specific way relative to the galactic plane to avoid being gradually perturbed over eons. Some astrophysicists suggest that galactic tides could have actually helped capture Planet 9 in the first place. The leading theory for its origin is that it formed closer to the Sun alongside the other giants, but was violently ejected outward during the solar system's chaotic early days. Instead of being flung into interstellar space forever, however, the gentle braking effect of the Milky Way's gravity, those same galactic tides may have slowed it just enough at the peak of its orbit to keep it bound to the Sun, trapping it in a distant, looping path. In this scenario, Planet 9 is a refugee saved from exile by the galaxy's faint embrace. Its very existence, if confirmed, would be a direct testament to an unseen dialogue between our solar system and the greater Milky Way, a reminder that even our most distant celestial neighbors are not immune to the whispers of the galactic ocean we all float upon. The faint whispers of the galaxy are not always made of light. A steady, invisible rain falls upon our atmosphere, and within it are particles of pure contradiction. Our instruments high above the Earth have detected a persistent, puzzling signal, an overabundance of positrons. These are the antimatter twins of electrons, identical in every way except for their opposite electric charge. When matter and antimatter meet, they annihilate each other in a flash of pure energy. Yet here they are, streaming from deep space in numbers higher than conventional physics can easily explain. The galaxy is not just a place where matter exists, it is a factory, actively creating and destroying its own antimatter in real time. So where is this exotic rain coming from? The hunt points to several spectacular suspects within our own Milky Way. One leading candidate is the pulsar, the lighthouses of the cosmos. These rapidly spinning neutron stars possess magnetic fields of unimaginable strength, capable of tearing particles from their surfaces and accelerating them to near light speed. In this violent process, they can produce pairs of electrons and positrons, spraying them into the surrounding space like a cosmic fire hose. A nearby pulsar could easily be showering our corner of the galaxy with these antimatter particles. But there is a more profound and more mysterious possibility. This signal could be the long-sought signature of dark matter annihilation. If dark matter is made of a certain class of theoretical particles like WIMP, then when two of these particles collide in the dense heart of the galaxy, they could annihilate each other, producing a cascade that includes standard particles like electrons and their antimatter counterparts, positrons. The detected positron excess could be the first faint echo of this invisible process, the ghostly fingerprint of the universe's dominant substance destroying itself in the dark. And we cannot rule out the most extreme engine of all, the supermassive black hole at the galactic center. The turbulent environment around Sagittarius, a star, with its intense magnetic fields and particle jets, is a perfect laboratory for generating matter-antimatter pairs through quantum processes. This steady drizzle of antimatter from the core would be a constant reminder of the violent physics powering our galaxy's heart. Each positron that strikes our atmosphere is a messenger, and its origin story is a cosmic mystery. Is it the byproduct of a dead star's furious spin, the death rattle of invisible dark matter, or the breath of a sleeping black hole? The answer is written in particles we are just beginning to catch, a silent antimatter rain telling the story of the galaxy's most energetic and hidden events. That silent antimatter rain is a message from across both space and time. Every single point of light in the night sky is a letter from the past, and this brings us to the final, humbling secret of our galactic home. We are not just looking out into space when we gaze at the Milky Way. We are looking back through a deep and layered history. We are cosmic historians, and our telescope is a time machine. The galaxy we see is not a single, coherent snapshot. It is a collage of moments from different epochs, all presented to us at once. The center of the Milky Way, that brilliant core anchored by Sagittarius, a star, lies about 27,000 light-years away. This means the light leaving that region today will not reach Earth for 27,000 years. Conversely, the light arriving at our eyes tonight from the galactic center departed 27,000 years ago. We are seeing it as it was when early humans were painting in caves, when the last great ice sheet still covered much of Europe. The black hole's quiet slumber, the frantic orbits of the G objects, the glow of the nuclear star cluster, all of this is ancient news. Now look toward the galaxy's opposite rim, the farthest edge of the disk from our position. That light has been traveling for over 100,000 years. We see that distant spiral arm not as it is, but as it was when our own species, Homo sapiens, was first beginning its journey out of Africa. The brilliant blue stars being born in the Carina Nebula, the violent supernova erupting in the Perseus Arm, the slow warp of the outer disk, each event we witness is stamped with a different date in the cosmic calendar. This creates a profound distortion in our understanding. We map the galaxy in 3 dimensions of space, but we forget the crucial 4th dimension, time. The elegant spiral structure we chart is an illusion of simultaneity. The inner arm we see might have already changed shape by the time its light reaches us, while the outer arm's light shows a structure that may no longer exist. We are assembling a puzzle where the pieces are from different boxes, trying to guess the present-day picture of a living, changing entity. This time delay makes every observation an act of archaeology. When astronomers detect a gamma-ray flare from the galactic center, they are studying an explosion that occurred before human civilization existed. When they measure the motion of a star cluster in the far halo, they are tracing steps taken during the last ice age. To understand the Milky Way as it is now, we must become master detectives, using physics to extrapolate from these delayed signals, to predict where things have moved and how they have evolved in the thousands of years since their light began its journey. It is a constant reminder of our modest place in the cosmos. Our entire recorded history is but a blink in the travel time of this galactic light. The Milky Way we know, the one we draw in textbooks and visualize in documentaries, is a beautiful phantom, a composite portrait of our home across ages. We are forever studying echoes, piecing together the story of a giant from the fragments of time it has left in its wake. This grand tapestry of delayed light reveals a single, unifying truth. Our galaxy is not a serene portrait hanging in the void. It is a living, breathing, and often violent entity, a dynamic system in constant flux. From its cannibalistic heart to its warped and wobbling disk, the Milky Way is a story of perpetual motion and hidden forces. We are passengers on a star that surfs a galactic wave, orbiting a black hole that once screamed its rage across the cosmos, all while enveloped in an invisible ocean of dark matter we cannot see or touch. The spiral arms are grand illusions of light, the silent spaces between stars are active recycling plants, and our own solar system might hide a refugee world saved by the galaxy's faint embrace. Every secret, from the antimatter rain to the echoes of ancient collisions, paints a picture of a home far more wondrous and strange than we ever supposed. So the next time you find yourself beneath a clear, dark sky, look up at that faint, milky band stretching overhead. Remember that you are not looking at a static painting. You are witnessing a predator's feast, a magnetic web, a fountain of million-degree gas, and the fossilized light of epochs long past. You are seeing a single frame in a billion-year epic, and you are a part of it. To keep unraveling these cosmic mysteries with us, be sure to subscribe. The universe still has countless secrets left to tell.